All right, ideal gas law. Uh, Ideal gas law is a law that combines the laws of Avogadro, Boyle's Charles, and Gay-Lussac's law. The equation for ideal gas law is PV equals nRT. So P stands for pressure, but for this equation, you have to have very specific units for it. So P is for pressure. In this case, it's going to be ATM. V is going to be volume, has to be in liters. Temperature has to be in Kelvin. N now represents our number of moles. This expression now can has the relationship when now where moles plays a factor into questions pertaining to gas laws. And R is what we call the ideal gas constant. It is 0.0821, and the units is liters times atmosphere divided by moles times K. The units is what dictates why we have to have these units for these variables over here because of this R. The ideal gas law tells you about a state of a gas at a current state, whereas the other laws that we've been using are when there are changes in the state of that gas from initial state to a final state. So let's do some examples here. All right, first example. It says here, calculate. Let me get my pen first. Okay, calculate the number of moles. So we want number of moles. Oops. So that's what we're looking for of a gas contained in a 3-liter vessel at 300 Kelvin with a pressure of 1.5 atm. So just like we do with all my other problems, we always write all our variables out. PV equals nRT. My pressure is 1.5 atm. My volume is 3 liters. My moles is what I'm looking for. That's my X. My R is always going to be that constant, 0.0821 liters times atmosphere divided by moles times Kelvin. And my temperature is at 300 Kelvin. Now I'm going to do a unit check just to make sure we're in the correct units. My pressure is in ATM, so that's good. My volume is in liters, that's good. I am looking for N, which is going to be my number of moles. My R is liters times atmosphere divided by moles times K. And my temperature is in Kelvin, so I don't have to convert any units to these units. They're already set. I'm going to write my equation, PV equals nRT. In this case, I am solving for N, so I'm going to box my N. I'm going to divide both sides by RT to isolate N. Okay, so there's my expression. P times V divided by R times T will equal N. So I'm going to plug in my variables. My pressure is 1.5. My volume is 3 liters. Divided by R, 0.0821. Divided by the temperature, which is 300 right here. Okay, so in my calculator, I'm going to hit 1.5 times 3 divided by 0.0821 divided by 300. And my answer will be 0.183. I'm going to follow sig fig rules, rounding rules, 0.183 moles for the first example. Okay, second example. Uh, Hit the video pause, try this one out. When you're ready, click start. So I'll pause for you to click pause and try this one out. All right, so this is another question, PV equals nRT question. I have 4 moles of a gas at a pressure of 5.4 atm that has a volume of 120 liters. And they want to know what the temperature is. So I'm going to make my list of variables, P, V, N, R, and T. Okay, my pressure is 5.4 atms. My volume is 120 liters. My number of moles is 4 moles. My R is 0.0821 liters times atmosphere divided by moles times K. And my temperature is my X. All right, so I'm going to write my expression. PV equals nRT. In this case, I am looking for T. That's my X. So I'm going to isolate my T. I'm going to box it. Divide both sides by nR. Whoops. I'll worry about that later. All right, so the n and the r cancel out. I plug in my variables. 5.4, 0 times my volume, which is 120. Why is it doing that? All right. Divided by n, which is 4, divided by my r, which is 0.0, oops, 0.821. All right, so I'm going to plug it in. My calculator, 5.4 times 120, divide by 4, divided by 0.0821, and my calculator, I get 1973 Kelvin, but I got 3 sig figs. So my answer will just be 1970 Kelvin, no decimal point, if you're following sig fig rules. Okay, third example. It says here, determine the volume occupied by 0.582 moles of a gas. So they want to know the volume at 15 degrees Celsius and a pressure of 52.7 kPa. All right, so going to write my list of variables. P, V, N, R, and T. Okay, my pressure is 52.7 kilopascals. My volume is X. My moles is 0.582 moles. My R is 0.0821 liters dot ATM divided by moles dot K. And my temperature is 15 degrees Celsius. Okay, so doing a unit check, my pressure is not in ATM, and so I have to convert. So kilopascals to ATM, so I'm going to convert that. For every 1 ATM is 101.3 kPa. So 52.7 times 1 divided by 101.3 kilopascals, I get an answer to be 0.5202 ATM. And I'm just going to carry it over 4 numbers out there. Moles are good. Volume is, well, we're looking for volume. R is good. My temperature has to be in Kelvin, so I'm going to have to add 273 to convert to Kelvin. Oops. And that's going to equal, add that to my calculator. I get an answer to be 288 Kelvin. All right, so now that all my units are in their correct number of units, I'm going to use my expression. PV equals nRT. In this case, I am looking for volume. So I got to divide both sides by P. Cancel those out. I'm now going to plug in. N is 0.582. R is 0.0821. The temperature is 288. Divide this all by my volume, which is, oh, sorry, now my pressure, which is 0.5202. Oops. Oh, my pen's going wacko. All right, so 0.582 times 0.0821 times 288 divided by 0.5202. I get an answer to be 26.5 liters. All right. Uh, okay, the ideal gas law is you can actually derive all the other gas laws from the ideal gas law. It is the one gas law that rules them all. The way we derive that is so here we have the ideal gas law that describes the gas at a specific state. So PV equals an RT. When we now talk about a gas at two different states, I'm going to use my little subscripts to signify that those variables can change for two different gases. So I'm going to use P1 V1 equals N1. R is always going to be a constant, so it doesn't get a 1, and T1. So by putting a little 1 at the bottom, that lets me know that those variables can change. In this case, all the variables here can change. The only one that never changes is R. So this is for one state of gas. When we're changing states, I'm going to put a 2 because now there's a change of state in a gas. So P2 V2 equals N2 R T2. So here we have the ideal gas law for two different states of a gas. Uh, let's say one signifies the original state and two signifies the final state. Now, I'm going to have some conditions here to how can we get the other gas laws given a certain conditions. And the conditions I have here is constant moles and constant temperature. Okay, so if those are constant, then what I'm going to do is I'm going to erase the moles, the little one here, because now it's a constant. And I'm also going to erase the temperatures. So since they are now constant, they don't get those little subscripts because now they don't change. So moles here, the 2 doesn't change and the temperature doesn't change. So those now are now constants. Okay, since they're both constants, we got what with the associative property of algebra. We're going to have all these variables here on one side and all our constants on one side. So I think the associative property is A equals B and B equals C, then therefore A equals C. So since this P1 V1 equals a constant and P2 V2 equals the same constant, then really I can relate these two. P1 V1 equals oops, nRT equals P2 V2. But since they're both equal to constant, therefore P1 V1 equals P2 V2. And this ends up becoming Boyle's law. Um, Pressure is inversely proportional to volume, but what has to be constant is our number of moles are constant, our R is constant, and our temperature is constant for this formula to hold true. So when we think about Boyle's law, which we've done in previous questions, there's actually some constants there that you're not seeing that has to be constant for this to hold true. Moles has to be constant, R has to be constant, and temperature has to be constant. And this, we're able to derive Boyle's law from this expression, given these conditions. Okay, so here I have another one. Constant moles and constant pressure. And so I know that my moles are constant, so I'm going to just erase these. This goes away. And my pressure is constant, so that goes away. Oops. So those numbers will go away over here. Now, to get these two equations to equal to each other, I'm going to put all the variables on one side. So I need to get the temperature over to this side and the pressure over to this side. So how I do that is I'm going to divide both sides by T1. So V1 over T1. And to get to the pressure on the other side, I'm going to get to the pressure over here. Whoops. So what's going to happen is I'm going to have a P, oops. Let me erase that really quick. I'm going to have V1 over T1. I've just moved my variables all to one side of the expression to where I get N R over P. So notice these are all my constants. They're on one side of the expression, and now all my variables are on the other side. And I'm going to do it for this side as well. So P2, oops, not P2, V2. All right, let's see. There we go. So V2 over T2 equals NR over P. So notice how my constants are on one side for each expression and my variables on another. And since they both equal the same constant, we're going to get V1 over T1 equals V2 over T2. So there we go. There's another gas law that we were able to derive from the ideal gas law. This is Charles's law. And with Charles' law, V1 over T1 equals V2 over T2, which is directly proportional. Granted that the moles, the R, and the pressure are constant when you're talking about this law. All right, I'd like you to try this one. Here's a condition, constant moles and constant volume. I'd like you to give it a try. So again, click pause the video, try this out, and then when you're ready, unpause the video. Okay, with constant moles and constant volume, so that means my moles will be constant. So I'm going to erase this and erase this. So the subscripts go away because they are constants. I'm going to put the variables all on one side. So I'm going to have P1 over T1 equals NR, uh, oops, let me erase that really quick. Wrong one. There we go. NR over volume, since volume's a constant. I'm going to do it for the other side as well. P2 over T2 equals NR over volume. Since these are both equal to the same constant, you'll see that now your variables will just equal to each other. P1 over T1 equals P2 over T2. And that ends up becoming Gay-Lussac's law. Gay-Lussac's law is directly proportional given that the number of moles, the R, and the volume are constant. Okay, here we have one condition where we have constant temperature and pressure. So click pause in the video, try this out. And when you're ready, click unpause. Okay, here I have constant temperature, so these go away. The subscripts go away. And then pressure is constant, so those numbers go away. All right, I'm going to have my variables all on one side, so I'm going to bring my n over to the left side. So I'm going to have V1 over N1. And then since I have constants here, it's going to be RT over P. I'm going to do this for the other side as well. V2 over N2 equals RT over P. Since I got two expressions with the same constant, they will relate. And now we're talking about a relationship that we don't really use too much in chem, at least in the beginning, in gas laws, a relationship with volume and the number of moles. And this relationship does hold true. You add more gas to a balloon, the volume increases. Given that the pressure is constant, your temperature is constant, and your R is constant, this relationship here holds true out here. So there's kind of a type of relationship here we don't always use, or always not written in books. Okay, constant temperature and volume. So I hope we're at this point we're getting to a knack of this. Constant temperature means that this becomes a constant. Subscripts go away, and the volumes go away since we have constant volume. I put my variables on one side. P1 over N1 equals RT over V. And I get P2 over N2 equals RT over V. And when you relate these two expressions, P1 over N1 equals P2 over N2 out here. So ideal gas law could derive a lot of formulas. And we'll just do one more for good measure. Constant pressure and volume. So if constant pressure and volume, these guys are both going to be variables. And let me get rid of that line. All right, so I gotta move, since those are constants, I gotta move my R to the other side for both of these. So I'm gonna have PV over R equals N1 T1. And I'm gonna have PV over R equals N2 T2. My constants equal each other. Those relate. N1 T1 equals N2 T2. Right, so I hope this helps show you how all the other formulas can be derived from this expression. In every formula that's used in the gas laws, there's always going to be a constant back there. So um, N1 times T1 equals N2 times T2. What is constant? Pressure has to be constant, volume has to be constant, and R has to be constant. So there you go. Hope that helps.